This meeting is being recorded.
Basically giving access to the students in that institutes, like Cadence is the biggest EDA tool for the chip design. So they are giving. So they are also they are productive to the okay, that is good. So maybe we start this. So like JNE also one of the part of that under institute, and we have some media tools like Cadence, then ADS, and then also Synopsys. Synopsys also we have on our center full bundle, that is 14 CAD, and also mostly our labs are device and fabrication and characterization. So we have this big equipments which is related to device separation like XRD. If you heard about that spectrum, so Raman spectroscopy, then TAM, then SAM. So this we have. So if anybody is working in device, so you can come. We are very nominal device we have done, and we are offering characterization. You can come and do your sample characterization for material if you are working in material utilization. So my field is not device. I am working on subject applications. So before joining the JNU, I was the assistant professor in NIT Karnataka. 6 years I was there, and we had tap out also. So some chips we tap out. Even I got I will show lecture. And then before that I was in South Korea. So South Korea, they have their own foundry, Samsung. Okay, Nano chip, and nowadays they are working 28 or 22 nanometer CMOS analog. Digital case we are talking in the world, we are doing 7 nanometer, even 2 nanometer. So, but I do not think we reach that circuit level and up to this level. I am up to this technology. I think they build wafers. Like recently, India also announced. India first chip we made at 2 nanometer. But how it can be possible? So they made a wafer at 2 nanometer. So wafer is what I am talking is you are I think you are aware about transistors, MOSFET. So MOSFET we have source, drain, gate, right? But that source of gate drain you are building in some base foundation. So what is that foundation? That foundation is wafer. So if I will start very initial time, who invented first IC? Anybody? No? Who invented first IC? That is the Jack Kelvin. Jack Kelvin 1958. Okay, first IC invented by Jack. After 40 years later, first RFIC, because the theme that is that's why here I am writing that high frequency engineering. So high frequency engineering is same RFICs, or I'm talking about NMIC. So first RFIC around 40 years later came into the market. That means I'm talking about in the year of 2000. So between 1960 to 2000, 40 years, what happened? So that time is like US, they built their own foundries, Intel, IBM. That time they building their processors. Then these Asian countries like Korea, China, they also became very popular to build up these chips, semiconductor chips. So high frequency chip came after 40 years later in the 2001, and that time researchers explored frequency range from 1 gigahertz to 5 gigahertz in the spectrum, RF spectrum. And say, at the same time, some researchers also explored high frequency up to 24 gigahertz. But nowadays we have the age of the wireless technology and mobile computing systems and our wireless communication technologies increasingly demand the use of small, tiny, high density RFIC and NMIC chip who can operate at millimeter wave band and some millimeter wave band. So how much range of millimeter band? Anyone? Microwave. Microwave start from 1 gigahertz to 30 gigahertz. Above 30 gigahertz is millimeter wave. Up to 300 gigahertz. Then above 300 gigahertz, some millimeter wave. This terahertz. So people are designing nowadays RFICs using some kind of millimeter wave band and some millimeter wave band. So in the year of 2001, when I'm talking, that time CMOS basically has became a popular for the IC design. Why? Because of cheap mass productions. So initially, CMOS chips, I mean RFICs, we made for the mobile communication. So after some time, it reached to Wi-Fi, then satellite communication, then radar. And nowadays, we are using RFIC medical application. And even everywhere we are using RFIC. Even your home also you are using RFIC. So RFIC, what is the base? Silicon wafer. You are studying the fundamental books, MOSFETs. So MOSFET, what is the substrate? Silicon. So that means the CMOS, that's why we are talking semiconductor chip. Semiconductor chips means that is making using the silicon wafer. And the standard wafer thickness is 0.5 micron when we started. But now we reach like news we are building 2 nanometers that wafer. And in that wafer you are building, like we are building up, we have some land. So land you are making some apartment. Same way we are making different stackings of the transistors. Okay, and we are building a chip. So today is my talk same based on that how we are designing high frequency, how we are doing high frequency engineering from silicon RFIC to GaN. So now question is why we are shifting? We are designing CMOS technology, our RFIC chips, that is silicon wafer. But now we are jumping to another process technologies. Why? Because if you see current MOSFETs you are using, so if I'm talking about amplifier, so what is the drain here? So amplifiers always operate in saturation, right? And what is the drain current? V1 COX W5 VGS minus VT whole square. So that means continuously our device is scaling down. That means we are going lower technology mode, like 180, 130, 45, 65, okay, 22, 28. So that is my channel. If your channel length is reducing, that means what your drain current is increasing. If drain current is increasing, means more power loss. So that means if you are going higher and higher frequency and you are continuously scaling down your devices. So we have certain RF performance and RF performance and RF power and performance extracts in CMOS. So that's why CMOS have several disadvantages in respect to power. So that's why people are exploring other semiconductor technologies. For example, silicon germanium. So even silicon germanium also now outdated. People are exploring gallium arsenide, indium phosphide, and now hot topic today in industry GaN, that is gallium nitride, which is a game changer. So we will see how it is. So now today I am going to deliver my talk. These are the outlines. So first we will understand what do you mean by RFIC and MMIC. So what are the design challenges and application? Then evolution trend of the technology, how to designing electronic system design. Then why we are shifting to GaN to silicon to GaN MMICs. And then I will introduce GaN HAMT, and then I will show my research reported publications. So what exactly we are doing nowadays in the market. So this is the brief research work. Mine. We are working in my research group in high-speed integrated circuits for wireless communication using various devices. We have worked CMOS, CNT, GaNMMIC, Gracing FPT for 4G, 5G, even 6G also we have IoT and optical communication. Also, we have designed on-chip antennas for biomedical application. Then we are working towards integrated circuit for neuromorphic computing. And then we are working also, we try to using hybrid technology to our ICs towards patient monitoring in the hospital. So right side you can see some of my hardwares, some measurements which we have done through our research areas. So if I would start very basic, so this is one side you are looking RFIC, and another side is MMIC. So what I mean by RFIC, radio frequency integrated circuit. That means you have chip, semiconductor chip, and you are operating at higher frequencies. Higher frequency is RF. When how range RF starts, which range RF starts? 300 megahertz to 1 gigahertz. That is the RF. So you are operating your IC and RF frequency. We call that is RFIC. Then another side we have MMIC. That is monolithic microwave integrated circuit. So what is the difference between RFIC and MMICs? RFIC mainly ICs we are using wafers, that is 4 group of periodic level, silicon, germanium. So you know, silicon is more superior than germanium, but combination if we will use, that is also we are getting some material properties better as compared to other materials. So we have 4 group of periodic elements, silicon, germanium, that we are using for the making wafers of that chip, and they are cheap, so that's why mass production is more. Application wise, you see, we are using for 5G biomedical satellite communication, UWB radar sensors. And if you see MMIC, that is monolithic microwave integrated circuit, where we are using compound semiconductor, which our theme, that is why we are shifting to semiconductor to compound semiconductor. So we have compound semiconductors like GaN, gallium nitride, indium phosphide, right? Then the gallium arsenide. So third and fifth group of the periodic table elements. So they are giving high performance. So application wise, if you see, almost same except one medical application. So MMIC is because operating at very high power, greater than 1 watt. So it is not suitable still for medical applications. So if you see RFIC always targeted main market advanced processes. Any foundry or any lower technology come into the market was captured by the RF. Like for example, recently South Korea announced they built one transceiver chip and 22 nanometer for 6G wireless. Still even we have 5G. Even other countries also in 5G. But they already starting work towards 6G. And 6G we don't know even bands. We not finalize our bands. But the South Korea they announced they already built one semiconductor chip with transceiver, right, for 6G wireless communication. So that's why at 22 nanometer. So any advanced process will come in the market first captured by the RF. MMIC is a unique market low investment process. That means it is demandable. Now we are working 5G. 5G we have 2 cells. One is micro cells, another one is macro cells. So macro cells we have high power demand. So that's why we are designing nowadays GaN based front-end modules. So we have demand like 5 watt to 100 watts for the base stations. So that's why we are designing GaN based front-end modules. So this is the RF design bottleneck. So first figure is showing what are the disciplines are involved to designing RFICs. Second is the trade-off parameter, which makes always multi-optimization problem for the designer when you're designing a chip. Like for example, you know that is power and frequency and gain. So always this bandwidth and gain is a trade-off. If you are getting higher bandwidth, your gain will be dropped. So you have to maintain both gain, also bandwidth also. So this kind of trade-off we are facing when we are designing that front-end modules. So what are the front-end modules I am talking? So this is the whole, you see, this is the general block diagram of class receiver architecture. I think you have studied in your BTech also. Intro and receiver. Intro and receiver you have studied of the communication system. That means a radio, talking about radio. So same kind of thing here. This is the class receiver architecture, where this bolded portion is the RF design. So this is the RF design front end. So we have antenna on a single chip, and this is the transmitter part where we have active component power amplifier. Same way, this is the receiver part. We have active component LNA, which is the low noise amplifier. Where we are using low noise amplifier? Anybody? Any more where you are using your mobile phones also you are LNA power amplifiers, right? Also, have told say DTH in home. Nowadays we have the DTH. You have the parabolic reflector antenna. Okay, so satellites you are receiving the signal, then it will be reflect. Then there is one ball. So that is we call a low noise block. So then that first received signal by low noise block, then it will be go to the contact cable in your TV. So there is set-top box. So there we have chip RFIC chip. So the receiver first component is LNA. So LNA, what is the use of LNA? Is suppressing the noise. Whenever incoming signal is coming from the space, we are suppressing the noise. So that is the function of low noise amplifier. Increase the signal strength. Okay. So because noise you can't remove from the system completely. So that's why you get suppress using some applying some techniques. So this is the RF content block. The major components, active components, I'm talking LNA and power amplifier. So here, what is the problem? RF content. So there are the two major issues because the signals we are receiving from the space, that is the major problem. You are transmitting, that is not much problem because you are transmitting the signal. So there is no noise problem. There is no much noise concern. Yeah, non-linearity concerns are there, but that we are take care with power amplifiers and we are designing. But majorly concerned when you are receiving the signal. So the signal you are receiving, that is very big. So that's why the major issues in RF circuits is two. First is non-linearity. So non-linearity basically affects your design unit, circuit design. So why non-linearity will again in your system? If you are receiving input signal which is too large. So if your input signal is too large and you are using MOSFET, right? In the chip you are using MOSFET for designing circuits. So MOSFET is a non-linear. So that's why non-linearity is there. So one issue is that non-linearity. And another is noise. That is minimum detectable signal. When your input signal is too small. So if I'm talking about the LNA low noise amplifier or power amplifier or filter, you have input and output matching network. And that input output matching network you are using tank circuit, LC, inductor capacitor. So when you take that LC, so it will be modeled by some parasitic R, that is resistor, and always noise will come in that resistor. So that's why these two major issues we have to take care. One is non-linearity, another one is noise. So for that, we have several parameters. Like non-linearity, if I'm talking, we have several parameters to calculate non-linearity, like IIP3, 1 dB compression point. Okay, and noise case also you are calculating noise figure, SNR, sensitivity. So these parameters, when we are designing this RF circuits, so these are the parameters we are uh, calculating all these issues, and we are taking care of to ignore the losses using that parameters. So स्टक हो गया ये है ना वो एनिमेशन थोड़ा डिफरेंट कर रहा था इसको ये वाला ना यस so this is the RFIC definition. You can see an integrated circuit made up of transistors, inductor, capacitor, antennas, which is operating at radio and microwave frequency. So this definition is 10 years ago, 1 decade ago. Now, if I will talk same RFICs, we have integrated circuit made up of nanotubes. We are replacing nanotubes with transistors because we are going lower technology nodes. So that is not support to the CMOS technology. So that's why we are replacing nanotubes to transistors, which is less than 9 nanometer. And strip lines, we are replacing with inductors. So why inductors? Because if you are designing one chip, we have one inductor and we have, let's say, 4 transistors, 4 inductors, sorry, 1 inductor, 4 transistors, 4 resistors, 4 capacitors. So this resistor, capacitor, transistor will take area occupied, same area occupied by 1 inductor. So inductors are very bulky. So that's why it is replacing slowly by the strip lines. So nowadays foundries like that is coming. We have RFIC where we are getting directly strip lines instead of inductors. Then long capacitors we are replacing because it is compatible with the MOSFET metal oxide semiconductor. So metal oxide metal capacitors. And I do not want to design separate antenna. So if I have one chip, I have to design one filter extra, then antenna extra. I do not want. I want all these components should come in one single die. I mean single chip. And you can see right side also this example. So this is the single chip RF transceiver where we have in single chip all web components, pads, antenna, receiver antenna, dipole transmitter antenna, then LNA, low noise amplifier, power amplifier, DCO, voltage control oscillator, buffer. So every component which you are looking now, previous slide, transceiver. So everything come into single chip and area also you can see that is 1.7 mm to 3.8 mm. Same way, this is 2-band LND, one block, low noise amplifier. So this 2-band LNA you are using in DTH in your home. Okay, that is 12 to 18 gigahertz. Then 2.4 gigahertz LND, we are using LND 2.4 gigahertz. Bluetooth, Wi-Fi. Okay, actually the range is 2.4 by 2.85. So that is your Bluetooth. So for that, this LNA and this RFIC basically includes sensors, amplifiers, data execution unit, mixers, oscillator, and on-chip antennas. And this is the band which I already told you. So these are the application areas of the RFIC. Famous RFICs for wireless communication, radar, air navigation, as I mentioned, you remote sensing. But nowadays, people's also working. I told you medical application. So if I will show you example where we are using medical application, so you can see we have brain and we have millions of neurons and we are talking with each other for electrically observable signal. So that electrically observable signal is a neural spike. So that exists in two parts. One is action potential, another one is local field potential. So range of that two signals, if I will talk about amplitude, that is microvolt peak to peak to millivolt peak to peak. If I will talk frequency range, that is millihertz to few kilohertz. That means frequency and your amplitude range is too small. So these medical professionals, doctors, they can't read out directly that spikes, which we are sensing through these electrodes. So this is the first step electrode, which we are implanting in the brain and sensing this type of neural spikes. This is so this is very why because very low in amplitude, very low in frequency. So that's why we are designing one signal processing neural chip where we have signal amplification, that means amplifier, low noise amplifier, signal filtering, then analog to digital conversion. So we are converting because that is the analog signal which you are sensing. Then you are converting to digital spike. Then we are assemble that all neural activities and using some machine learning or AI techniques, we can extract some meaningful information. Then we can modulate that signal and give to the implanted antenna, which we are implanted at the top of the brain layer, that is skull. So that implanted antenna sending towards the reader application, the reader side, I mean some receiver application, which can be anything, your mobile phone, prosthetic device, your maybe a laptop, computer. So where you have reader antenna and you are receiving using the WPT technique, wireless power transfer technique, that signal. And then we are doing brain mapping to effectively track and decode your user experience. So like that, one of the example where you see so many areas are there. One is electrode design, another one is specialized IC design, another one is image processing or data processing, another is microwave, that means your antenna design, and one part is wireless data power transfer system also. So another example, so this previous example we did in our Indo-Korea project, and recently that finished that project. So we build one UL chip for the signal processing. And this is another area which we worked, and we did 2 patents. Already this technology 2 patents scheme. So this is idea is same, like blind people's. For blind people, we have designed one retina neuron chip, which can interface between wireless power devices and then implanted neuron for the image visualization. So what is the idea? The camera which is captured this image, and camera is giving output at the RF. So the our eye, we are wearing that contact lens. In that contact lens, we can put first antenna, which can receive that RF signal and convert it into DC signal. Then we are giving to RF harvesting circuit. That means rectifier, which can convert into DC, and then that DC we are giving to some LED, which provides some light, and which is going inside where photoreceptor layers are there, and where we have implanted a CMOS neuron chip. So the light is receiving from that CMOS neuron chip, and then output is providing number of spikes. So if number of spikes is more, so image biological image acquisition is more. So that is the idea which we gave in this biomedical application. So we already recognized by Times of India, India TV, Ministry of Education also. And as I mentioned you, 2 South Korean patents also granted on this same technology. We have implanted also in mouse. So you can see we have used 65 nanometer CMOS technology, and UWB band we have biocompatibility telemetry, frequency range 3.1 to 10.6 gigahertz, and our efficiency we got 70%. Same power harvesting IC we design, efficiency is 40 to 80% we got. And then CMOS neuron retina we design. We use SoC technology, silicon on chip, and chip area we got this much, and power consumption is nanowatts. So application is retinal image execution. So now question is come, how to design such kind of IC? What is the first step? Like sir told now, future college also collaborative with ITZ. Maybe you will also get exposure there. How you will design? So this is the first step you can understand here. So how to design? First, because you are the customer, so you should have your specification. Like for example, I want to desigin low noise amplifier for Bluetooth application. So what is the first specification? 2.45 gigahertz. That is my frequency range. Another thing, I want gain greater than 15 dB. That is my second specification. Third, I want power consumption, let's say less than 10 milliwatt. That is my third specification. I want gain more than 20 dB. That is my fourth specification. I will take source and node 51. Okay, so like that I will make my specification. Accordingly, I will go manufacture. Who is the manufacturer? TSMC, Taiwan Semiconductor Manufacturing Corporation. Like that, so many are there. Global Foundry. Now India also, SCL 180 nanometer. Let's say you write same manufacturer, and they will provide you PDK, process design kit. So that is CMOS 180 nanometer. So now you have to design with your specification circuit. Okay. So what you will do, you in that PDK you have models, you have layouts for simulation and that layout to make the layout of your design. So what you will do, you will build your circuit schematic. You can put in architecture and check your specification. If it is good, then you can go for simulation your circuit. Once your simulation you will get, then you can place in the layout. So you can build the layout of your circuit. So once layout, after that you can do post layout simulation. You can check LVS, DRC. If everything is working, that means your pre simulation, post layout simulation also matched. So then you can send same layout file to the Gerber file to the manufacturer, same manufacturer, semiconductor model. So they will build chip, and after that they will send to you. So in your lab environment, then you can test it, and you can check whether you are getting same specification or not. If you are not getting, means your money is waste, because you are paying, let's say I am paying TSMC 180 nanometer. Nowadays rate is if I am going 1.5 into 1.5 mm square, so I have to pay 2 lakh for up to packaging. So if my chip is not working, that means 2 lakh rupees is waste. So for our case, 2 lakh rupees is very big money. But if I will talk about like those are already built foundry 2 years, 2 decades ago, or 1 decade ago, they don't much take care of about one chip fate. Okay, like China, Korea. So 2 lakh rupees here means there is 2000. So 2000 rupees is nothing as compared to 2 lakh. So this much expensive to make a semiconductor chip. So that's why you have to take care before you are tap out your chip. So this is the design stages. Same thing you can see in pictorial view. You have system specification. Based on system specification, you have to do modeling of device. Then you can build schematic. If your schematic is working, then you can go architecture. You can check your specification. After that, you can go for layout for same schematic, and then you can send for manufacture. Then chip will fabricate, and then you can test it, and you can use for same application. So we have three types of analysis there. Model level. We are doing device modeling, then circuit modeling, and then after that behavior modeling. So this is the one of the example. This is the RF layout. So in layout, you can see this is the inductors. Then some MOSFETs are there. Then this is the testing pads where you are putting your VDD or VCC, I mean ground, input, output, RF output. Then after that, your chip will come like this. So this is your chip, and this is your golden pad. This is your testing pads. Okay, so this is the number of pins basically. So here we are putting our bonding wires for test the chip. So if you see, we are not looking anything inside this chip. So if you take microchip photograph, then only you can come to know what is the microchip photograph. So if I will show you my chip, so this is my chip only. We did in COVID. So this is the after packaging. This is the chip. So that is the chip, and this is the golden pad, testing pads. So this is the LN basically low noise amplifier. So this is the microchip photograph you can see. Then after that you can test it in the lab environment. So this is the DUT, which is your chip device under test, and because it is a two-port device. So two-port device means you have to, and higher frequency you have to calculate what test parameter. So you have reflection parameters S11, S12, VSW are same. Transmission parameters, that is S12, S21 transmission coefficient parameter we have to test. So using this equipment, we are testing. First is VNA, vector network analyzer, and RF power station also. So this is the total two-dimensional process innovation. So you have to do device theory, circuit theory, system theory, application theory. Then you have to do modeling, device modeling, circuit modeling, system modeling, application modeling. Then you have to design device, circuit, system, application. Then you have to simulate also again device, circuit, system, application. Then you will get your desired specifications. So total, this is the involved when you are designing the circuits. So this is one of the example. If I will talk about CMOS technology, not GaN. So CMOS technology, if you see, this is the one of the proposed block diagram where we want to monitor the patient actions in the chamber, medical chamber. So for that purpose, we are using UWB radar. And UWB radar, we know we have one is transmitter section, and another one is the receiver section. And the right side, you can see this is the that the signal where we are fluctuation means patient movement is there, and where signal is rest, that means no fluctuation means there is no movement in the patient. So we are monitoring using this UWB radar. So this UWB radar, what is the problem? The infrastructure IC solution which we are using, it is not upgraded. So especially when we are sending the signal, transmitter side, we are sending signal towards the patient. So that signal is come contact ceiling of the patient, then it will be reflected back. And then if we found fluctuation, that means we are assuming patient moved. That means patient is doing movement. And if it is unrest means it is not fluctuation. So what we have to do, because we have to send the signal toward the patient, that should be a proper UWB signal. That means ultra wideband signal. So the power amplifier, what we are designing, we have several limitations because that power amplifier we are designing using the CMOS technology. So we have several limitations. So like you can see right side also, what is the trade-off? So usually we are designing power amplifier using such kind of topologies. You know about this. This is the cascode, right? Common source cascode. So this is the cascode, and in that cascode, what is the trade-off? What we are observing? If you are going lower and lower technology node, so what is first is this one power efficiency. So power efficiency goes down. Same way, if you are going lower technology node, that device reliability also goes down. So that means we have to take care about trade-off between device reliability as well as device length. Sorry, device reliability and power efficiency. So the major component of the, parameter of the power amplifier is power efficiency and drain efficiency, and also output power. So CMOS, we have very limited output power, which can be given to the antenna, and antenna then transmit the signal. Because CMOS maximum power you can get is milliwatt. Then another disadvantage I told you, if you are going lower and lower technology node, current will be increased. So that's why power loss also is more. So device power consumption is. So it is not enough power. So but because when we did this work, that time we had a one option only. We have to do anyway. We have to design CMOS power amplifier. So some techniques we applied there to overcome that trade-off between device reliability and power efficiency. So like first design we incorporated several things in that cascode topology, like the T network, shunt capacitance, series inductor, then output matching network. And even we did also modeling, small signal modeling for that. And so I will not go much deep. So this is a fabricated chip of design. And if you see comparison table here, so we compare, we designed 65 nanometer, we got 3 to 11.7 gigahertz band. and then 40 dBm is the peak output power. Then gain also 20 dB. The drain efficiency is 73%, power efficiency 80%, and chip size is 0.3 mm square. So what is the problem? Problem is bandwidth. Because I told you we have to get, this is the UWB radar, and it will send the signal at the UWB signal, UWB range. So that UWB range already we got from the CMOS power amplifier. But what will happen in practical scenario when we integrate same power amplifier to antenna? So there is a loading effect. Because of loading effect, my bandwidth is degraded. So that's why I'm not getting proper UWB bandwidth. So to maintain that proper UWB band, then again we optimized our design too with some re-engineered incorporations. So we have applied here negative capacitance technique. Then we also incorporated one more stage, that is class F1 inverse. Then again we fabricated and we tested. So now my band we are getting 2 to 13 gigahertz. So now we are getting enough band. If even if we will integrate with this antenna, loading effect also will come. Still we have we observe during the measurement we have still proper UWB band to send the signal. So like that we optimized that power amplifier in UWB radar. Then we compared also both designs, and this is now. So what is the problem? First problem is we have seen here we have limited output power. You see power added efficiency also 85%. I mean drain efficiency 75%, and power also not much, just 40 dBm. So we need also more power because we are sending through the antenna. Antenna wants more power as an input to send continuously power in a long term. So uh, we have another best candidate alternative, that is the GaN. So we have this various semiconductor materials, semiconductor process. You can see nowadays we are using gallium arsenide, silicon already we are using CMOS. Then we are using nowadays combination of these two, GaN plus silicon carbide. So what is the most important concern here is electron mobility. So electron mobility of the device closely relates to the achievable gain and noise performance of the device. So if we will see, highest mobility is the gallium arsenide. If you see, that is the 80, it is in meter square per volt second. If you calculate centimeter square volt second, it is the 8500. And it is gallium arsenide is the highest as compared to gallium nitride, which is 1800, and even in indium phosphide also 15400. But if you compare GaN as compared to silicon, and if I will combine silicon carbide and gallium nitride, the electron mobility is high as compared to silicon. Another important aspect is band gap. We know energy band gap, which is the difference between valence band and conduction band, and which defines the breakdown voltage. So that means if you see breakdown voltage of this gallium nitride, which is the high breakdown voltage, and that is because electron gap, that is energy gap, is too high as compared to gallium arsenide as well as silicon. So I'm telling you now we are combining to both to make a GaN HEM device. So if you combine both band gaps, you will get very high breakdown voltage. So very high breakdown voltage means you can handle high voltage and high power handling capability of the device as compared to silicon. And another important factor is thermal conductivity. So thermal conductivity, what implies, that is the heat dissipation of the device, and that directly relates to the device power consumption. So if you see here, thermal conductivity is very high of GaN device as compared to indium arsenide also, even silicon also. So silicon also 145. Sorry, if we will combine silicon carbide and gallium nitride, so total that thermal conductivity is too high as compared to silicon as well as gallium arsenide also. So thermal conductivity is high, thermal resistance is low, So that means device power consumption is better as compared to CMOS. So why this gallium nitride, now gallium nitride had game changer technology in industry. So if you see here, this is the RF content module. So when you are designing using the CMOS, silicon germanium or gallium arsenide, uh, using these semiconductor materials. So what is the thing? You need additional protection circuits. For example, circulator, isolator, or limiter at the receiver end. So which directly degrade the noise performance. Also, they are increasing the design complexity. So to avoid that, what we are doing, GaN, we are using with SPDT, that is the single pole double throw switch. So here you do not need extra additional protection circuit. So it will be reduce the design complexity, and also it will reduce the cost. So even you can make single chip with GaN power amplifier, GaN LED with SPDT along with antenna. That can be come in the single chip and with very low cost as compared to CMOS. And the right side figure you are looking. So right side also you can see, especially for 5G system, satellite applications and space applications. Thanks to GaN power density, which is more dominating high power, 2 to 7 gigahertz band, and also greater than millimeter wave band, 24 gigahertz. So gallium nitride is the most dominant technology for high power handling capability. So if I will talk about GaN HEMT, so first HEMT introduced by 1970 Dr. Takashi, and it was developed for low noise amplification, low noise applications. And this is the noise figure. So one of my PhD student, he worked on already, he already awarded one PhD degree on this technology. He developed 4 LNAs, GaN based, and 2 GaN based power amplifiers in his PhD work. So his PhD work only, so this is the minimum noise figure we are getting here. So this is the cross-sectional view of GaN HEMT, what we designed our GaN HEMT. So that is the cross-sectional view of that. So you can see the substrate, that means foundation of this GaN HEMT is silicon carbide. So we are combining GaN and silicon carbide, and we are making this transistor, gallium nitride, high electron mobility transistors. And this is the you can say small signal equivalent model of this GaN HEMT cross-sectional, and that he derived some current and voltage equation. So we did this first work for the marine communication. So this is our specification. We design frequency range. We have taken 0.5 to 2.7 gigahertz. Voice band we want greater than 5 megahertz. Noise figure we want less than 1.5 dB. Gain greater than 15 dB. Power approximately 40 dBm. Power dissipation less than 400 milliwatt. Stability also greater than 1. So we proposed first this broadband matching circuit, and we applied here even and odd techniques. So one time we calculate in even mode, another time we calculate in odd mode. So with this technique, we basically getting the best matching circuit in our power amplifier, our in GaN HEMT LNA. So this is the even mode equation, and this is the odd mode equation. We model that equations, and then we are getting S parameters, reverse isolation, forward isolation, transmission coefficients values. So this is the finally that circuit, broadband stage circuit and inverted broadband stage circuit, we have incorporated our along with that GaN HEMT device. This is the GaN HEMT device, and we built our LNA circuit. So this is the layout, and this is the fabricated view. So this is the results we got. If we will directly come to this table, so you can compare other technologies which already reported. So we applied high voltage, as I told you, high breakdown voltage of the GaN and silicon carbide. So it can handle up to 28 volt, even more than that also. And frequency range is 0.5 to 2.7 gigahertz. And gain we got 17 dB. Noise figure is very ultra low noise. We got zero point 0.6. Output power also 40 dBm. And power consumption is 120 milliwatt, and area is 32 to 26 mm square. So then further we went another work, because that specification is approximately up to CMOS. So that's why we developed again one GaN based amplifier. So in this case, we first developed our GaN ham device. We made our GaN ham device. So this is the GaN ham device where we applied slotted technique. So we generated 20 watt, 25 watt of power from this device itself. And this is our specification. And then after that, we build our circuit here. So this is the circuit, our proposed LNA circuit, this final schematic, where same our this 0.15 micrometer, 150 nanometer GaN ham device, we modeled and we fabricated, and we incorporated in our circuit. And this is the matching networks. That is, we applied DGS techniques, defected ground technique, and we generated this matching network. We incorporated this LNA, and after that, we got performance here. You can see this one. So now you can see here, now we are getting two bands. One is 1 to 1.4 and 2.1 to 2.9. And frequency range 1.17 and 2.459. Noise figure, ultra noise figure, we are getting 0.7 and 1.6. Gain also 14 to 11. And now this output power we are getting 43 dBm. So it is about to be 25 watt. So this is, and then power dissipation also very low, 22 milliwatt. And FOM also very high, figure of merit. Then we have done one more work, that is a rat race coupler based compact GaN ham power amplifier towards flat high efficiency over broadband. So always there is a trade-off between power efficiency and broadband. If you have wide bandwidth, then power efficiency goes down. If you have high efficiency, then you have a band is narrow. So that's why that trade-off we try to optimize through this design. So here our frequency range is 1.6 to 3.6 gigahertz, which is wide band, greater than 5 megahertz. And power added efficiency also greater than 55%, drain efficiency more than 60%. So like that specification we made, and then we designed our rat race coupler. So rat race coupler, I think you have studied, that is the microwave component. So that microwave component, that is the 4-port device. So this 4-port device we modeled with the RLC techniques, and then we optimized first this RLC rat race coupler, and the same thing we have incorporated along with GaN ham, and then we locate same our fundamental frequency and higher order frequency to the Smith chart. And then after that, we have built final. This is the schematic of power amplifier with this RRC and then we fabricated also MMIC. We did MMIC fabrication for this. So this is the values we are getting. Now you see drain efficiency up to 85%, power efficiency also 74%, even wide band 1.8 to 3.6 dB, and output power up to 46 dBm. Very high power. It is about to be 30 watt. So then we compare. So this is our developed 40 watt 0.15 micrometer GaN ham MMIC using a rat race coupler. So this is some my memories with Korean lab, which usually we are using that foundry only for tap out that chips. Thank you. ADS So I think I know you are the beginner in these things, but this is actually required for you. Always you are running the AI and you should be not forget our course